Hi, my name is Akuya Abu, and for this video we're going to go through the method of separation of variables as explained by Greenberg. So the basic process of separation of variables can be really characterized by the following steps. First of all, we know that in separation of variables we're going to seek a solution of the form u of x at t equals x of x t of t. And we're going to plug this into our partial differential equation given, and then divide both sides by x of t. Then the result will be set equal to a constant, negative k squared. And then we will solve the two resulting ordinary differential equations, apply our boundary conditions to get a general solution, and then initial conditions for a more specific solution to the problem. So we can illustrate this using Greenberg's example 18.3.1 within the text, in which he starts off with the following diffusion equation written here. So again, as the first step, we're really just going to continue to use the solution of the form x of x t of t. And we're going to plug this into our diffusion problem to get the following relationship right here. Then we're going to divide by our xt, and that gives us the following relation, which we can set equal to negative k squared, as both of them, as you see on both sides, you've got the different variables isolated to their different sides, which do not depend on each other. So, yep, setting it equal to the constant over there. So then after that, you can see that this can break down into two different ODEs. The first one taking into account x, and the second one taking into account t. So that gives us the following two different ordinary differential equations to describe the system. So then we solve these ODEs, noting their general forms for x equals a cosine kx plus b sine kx, and for t equals to a constant times e to the power nk squared alpha squared times t. So then we note that these two forms are actually not the most general case, because they actually only hold when k does not equal 0. So in order to actually take into account when k equals 0, we note that for at least for the x, you also have to include the case d plus ex, and then for the t case, g. So therefore, those more completely characterize the entire system. So then we will plug in our expressions into the solution, which we have already knew is of the form u equals xt. So then if we take those and we just plug in the relations that we got above, and then we simplify, you get the resulting relationships here. So then the next step is to apply the boundary conditions to what we have. So for the first boundary condition given, u0t equals u1, so you're going to plug that into the relations given and simplify. So we see that we've actually figured out the values of the constants h and j. And then we just do the same thing with the second boundary condition, ult equals ut. So this one actually decomposes, and you get it into the form k sine kl equals 0. So then you have a choice here in which you can actually just trivially make k equal to 0 or sine kl equal to 0. And as Greenberg notes as a rule, we usually choose the more robust solution, which would be sine kl equals 0. So then moving on, we actually take that and we can apply that to get our general form. So we have from before, k equals n pi over l, where n is any positive integer. And then we plug that into our regular form for u, and you get the actual relation for uxt, which would be our most general solution. To get the more specific solution, you just impose the initial conditions. So the initial condition given, which was u of x0 equals f at x. So then if you just plug that in to the different, to the relation we have, and then just clear it up a little bit, you actually get the following relation as a specific solution for the specific diffusion problem. And Greenberg also notes that it's actually the form of half-range sine. So then Greenberg goes on to explain a couple of things regarding the constant k-squared term over here. For instance, in 18.3.2, at the back of the section, he explains this problem, which goes on to relate the sign of the constant. So the question tells us to show that if we use k squared instead of negative k squared, that we will eventually arrive at the same solution as before. And actually, Greenberg notes within one of his comments at the end of this example that the rule of thumb would be to choose a sign, whether it be positive k squared or negative k squared, but then to look at the ordinary differential equations that arise from that sign to see which one would make more sense and be more logical and easier when solving the problem. But the problem is generally solved in the same way. So we're still looking for a solution of the form u equals x of x t of t. So we're still plugging it into a diffusion equation and dividing by xt. So far everything is the same as before, except over here after we divide, we're setting it equal to k squared instead of negative k squared. So from there, you go back and you get your two different ordinary differential equations, a little bit different because of our sign change. But we go on as usual. We solve the ordinary differential equations. You can see that they are more complicated in this case. They actually go down to hyperbolic functions to take into account of the imaginary components that this choice actually gave us. So then, but I guess the same way, you keep figuring out exactly how to express x and t, and then plug that into your general solution u equals x of t. Over here, we're plugging it in, and we are renaming the constants that come out, the C, D, A, and B, just to take into account of the multiplication operations from before. But then after that, you're going to apply your boundary conditions as before. Here, you're getting different results just because of the different problem. And again, we have a choice over here when we have our k equals n pi I over L term, and we're choosing the one that actually would make the more robust solution. So then we right now finally have the general solution for our equation u of x of t, and you can see that it is actually the same as before, except you can see that the form is a little bit different. You have an imaginary component within the solution, but you can, if you look to the other solution, you can recognize that if you just substitute that out for a constant, you really do have the same thing. So yeah, so from this you can see that the sign of the constant really should be noted. It really comes from the ordinary differential equations, just picking the one that is more logical to solve the different equations. So over here, it was easier to do it with the negative k squared, but the k squared form would actually also work. The second part of this equation, of this problem, actually just tells us to show that in Storm-Liouville form that the k squared has to be non-negative within our choice of negative k squared for the constant. So then if you look at example 3, actually in the same section, Greenberg notes how we can take this to Storm-Liouville form. So here we have one of the general equations that we got from doing the example 1, and he notes that you see in this term you've got the orthogonal eigenfunctions of a Sturm-Liouville. So that actually goes down to the following relationships, which are actually in Sturm-Liouville form. So you noting its Sturm-Liouville form, P equals 1, Q equals 0, and the weight also equals 1. And you're supposed to treat K squared as the lambda term that you usually have in Sturm-Liouville form. So then if you look to some of the theorems posed later in the book, posed earlier sections in the book, it states that if you have a Q that is less than or equal to 0 on AB, and P of X times the eigenfunction and its derivative, if you apply that on the range A to B, and that's less than or equal to 0, then not only is your eigenvalue real, but it's also greater than or equal to 0. So from that, and just noting that that's what we actually get within this relationship, you actually see that the K's over here must be non-negative, just relating the theorem. All right, that's it for this example. Hope that was helpful. Thanks.